Hi, this is Mark Weitzman. Welcome back to my channel, Theoretical Physics with Mark Weitzman. I'd like to continue with Lesson 9 of Quantum Field Theory, A Student's Perspective. This will be Part 2. So we have Lesson 9, the path integral for interacting field theory. This is Part 2. In this part, we're going to focus on just organizing what are like connected disconnected vacuum diagrams. And we'll find that the path integral can be simplified. So let's just start by defining terms. Connected means just what it says. You can trace a path through the diagram for any 2 points. So something like this is connected. Something like hold on 1 second. I want to get some vacuum diagrams. They're also connected. Basically, all the diagrams Shigneki shows something like these. So this and this, these are all connected. And disconnected just means a sum of a finite number of connected diagrams. So oftentimes we might sum like all the 2-point, and we might have a diagram that's like this plus this, plus let's say this. These are all disconnected, so this is a disconnected. And it's like each individual one is connected, but you can't get from one to the other. And we'll label CI with an index I stands for a particular connected diagram, including the symmetry factor associated with that diagram. So this is, just an index by I. There are, of course, an infinite number of connected diagrams, but we can label them by an integer I, going from the simplest to the most complicated. A general diagram let's call it D. Well, I'll give the formula first and then explain it. 1 over SD, the product over I. Symmetry uses a capital I for the index here, but I'm going to forget a lot of times. CI to the NI. Now NI is an integer, that counts the number of times that CI occurs in D. And SD, this is the additional symmetry factor for the diagram D. Okay, so it doesn't include the symmetry factors already included in CI. That's why we said we included CI includes the symmetry factor. So now, what we're doing is we're sort of saying, let's say we have this diagram which has a symmetry factor of 2, and this diagram which has a symmetry factor of 2, and this other diagram which has a symmetry factor of 8. What other symmetries can we get in these diagrams? What exchanges can we make that we haven't counted for? Well, it's kind of obvious that we can't do anything between like the first double source diagram and the last no source diagram. We can't do anything here because there's no way to line it all up, and it will just change the connected diagrams. It will change the total diagram. But we can do something between the first and the second. We can exchange between here and here, here and here. We can do things like this, and things like, on the outer and the inner. So there's lots of symmetries we can do here, but there's two things that we have to do. And this is fairly easy to see when you think about it. Exchanges must be made among different but identical connected diagrams. And 2, the exchanges must involve all of the propagators and vertices in a given connected diagram. So in other words, we can go between the first diagram and the second diagram, but we have to completely exchange one whole diagram with another. So this implies, it's very obvious, that to make these arrangements, we have ni factorial. So for instance, if we have two diagrams, we'll have, like as we showed above, we'll have a factor of 2 for the new symmetry factor. But if we have 3 diagrams, I can exchange the first diagram with the second, the first diagram with the third, the second diagram with the third, I can get a total of 3 factorial. So so okay, to make these rearrangements. So this implies that the symmetry factor is equal to the product over I of ni factorial. So each, if you take the ith diagram, and there's like 7 diagrams in there, we can make 7 factorial. And then if you take the I equal 9, the ninth diagram, and there's 3 in there, 3 diagrams in D, then we can do 3 factorial rearrangements for those. So that's what we can do. And so we have this new symmetry factor calculated. So each general diagram is labeled by integers ni. And for example, like if ci, the connected diagram corresponding to integer I, doesn't occur, doesn't occur in D, then ni equals 0. If it occurs once, it's once. If diagram number 123 occurs 36 times, then ni is 36. So that's just notation. That's all we've really done is notation. Now we go back to our z1j, and it's proportional. And I'm writing proportional because eventually we're going to have to enforce the condition sort of by hand. z1j at j equals 0 equals 1. That's our normalization condition. But z1j is basically proportional to the sum over the set, all possible sets of integers, ni of D. So this just stands for, it's saying n1, let's say we label the diagrams from 1 to infinity by the natural numbers. And it's basically saying n1 might be 5, and 2 might be 0, and 3 might be 0, and 4 might be 0, but n5 might be 1, and 6 might be 2. So it's all possibilities for assigning an integer value to ni for I equal 1 to infinity. And this is proportional. Let me label this equation 1. And this is proportional to the sum over the sets of all possible sets of ni. D, as we said, we showed above, that it's the product over all I of 1 over ni factorial ci to the ni. So I might have confused you a little bit above when I was talking about disconnected diagrams. The diagram corresponding to this it's not an addition here. I wrote it as just like the diagrams that occur in there, but it's actually the product of one diagram. For this whole diagram, it would be the mathematical expression corresponding to the first times the mathematical expression corresponding to the second times the mathematical expression corresponding to the third. So I think I might have misspoken earlier. But as I said, we have a symmetry factor associated with the total new diagram D, but it's the product of all of the connected diagrams. If they, we're just multiplying them out by how many connected diagrams occur, and then we segregate them according to ones that are the same. So this is the product over I of 1 over ni, ci to the ni. I'll label that 2. And this is proportional. Now you can invert these products in sum, and I'll talk a little bit about that later. The product over I, the sum from ni equals 0 to infinity of 1 over ni factorial ci to the ni, 3. And this is proportional to the product over I of, this is the usual exponential Taylor series, the exponential of ci, and this is proportional to the, so now we're just using the rule for adding exponents, the exponential of the sum over I of ci. So this is what the path integral, not including the counter terms, but including the interaction term. Okay. So the only shaky thing was from 2 to 3. Not really shaky, but if you've never seen it before, you might go, wait a minute. Here we have sum over all possible sets of integers. Now we have ni equals 0 to infinity. I'm not sure about this. So all you have to do, so 2 to 3 works, but you can see this by explicitly writing it out for for a specific set of diagrams. And once you see it, you'll see that it works all the time. So let's say that there are only, we live in a universe with only 3 connected diagrams. Of course, we don't live in that universe, but so then we have the sum over the sets of ni, product over I, 1 over ni factorial, ci to the ni. So this is basically equal to the sum. And we only have 3 connected diagrams, so we only have 3 integers, n1, n2, n3. Product from I equal 1 to 3, 1 over ni factorial, ci to the ni. Okay? And this is equal to the sum. Remember, we take all possible values for n1, n2, n3 among the natural numbers. So we have like the sum from n1 equals 0 to infinity. The sum from n2 equals 0 to infinity. The sum from n3 equals 0 to infinity. And then we have, and explicitly write out this product, 1 over n1 factorial, c1 to the n1, 1 over n2 factorial, c2 to the n2, 1 over n3 factorial c3 to the n3. Now let's take what we need it to be, what equation 3 is, which is the product from I equal 1 to 3 I equal 1 to 3, the sum from ni equal 0 to infinity, 1 over ni factorial ci to the ni. So this is just writing out the outer product. We're going to have the sum from n1 equals 0 to infinity, 1 over n1 factorial c1 to the n1. Sum from n2 equals 0 to infinity, 1 over n2 factorial c2 to the n2. And then sum from n3 equals 0 to infinity, 1 over n3 factorial c3 to the n3. Okay. Now, if you just expand this out as you were doing, it's a bunch of sums times a bunch of sums. So we can have one term here, one term in the middle, and one term in the final. So this is just the sum from n1 comma n2 comma n3 equals 0 to infinity of 1 over n1 factorial. We take 1 from here, c1 to the n1, 1 over n2 factorial, c2 to the n2, and 1. Remember, we're taking a specific integer here, but we're summing over all of them, so we're going to get all these terms. 1 over n3 factorial c3 to the n3. And these two things are exactly the same. So, just in case that bothered you, it bothered me when I first saw it, but I wrote it out like this, and then I was okay. So now we have to enforce. Okay, so we still need to enforce z10 equal 1. Okay. Well, now we see that it's easy to do. Okay, to do this, we simply omit vacuum diagrams, those with no sources. So diagrams such as that, we simply leave those out of the sum. Now, you might think this is like we're changing our equations or our formulas, but think about it. We have zj, we have z1j, which is given by it's proportional to e to the sum over I of ci. That's what we derived, that nice looking formula. Now, since it's proportional to that, what that means is z1j is equal to, let's call it alpha, some constant, times e to the sum over I of ci. Okay. So now we can write this as, and we also know, we can write this as z1j is equal to alpha times e to the sum I'll write I unequal to 0 of CI plus the sum. I just want to check one thing real quickly in the textbook. I'm using the same notation that he is. Okay. Plus the sum of, I'll put it a sum over vacuum diagrams of CI. So what I'm doing is I'm separating out all the vacuum diagrams from all the diagrams with sources. Ion equals 0 means that there's no vacuum diagrams in here. So a vacuum diagram is a diagram with no sources. So now let's see what Z1J equals 0. Z1, 0, which we want to equal to 1, is now equal to alpha. J equals 0, E. Now, the sum of all the non-vacuum diagrams, they have sources. So when you put J equals 0, they all are 0. So I have E to the 0 plus the sum over all the vacuum diagrams of CI. So this is just equal to alpha E to the sum over the vacuum. This is not the best notation, but I'm just going to use it for now. And this implies that alpha is equal to 1 over E to the sum over vacuum diagrams of CI. So now we go back to our Z1J, plug that in. I'm doing this in a very obvious way, but let's go plug it into this. It's equal to alpha. We've already evaluated alpha. 1 over the sum over vacuum diagrams. E to the sum over vacuum diagrams of CI times E to the sum over non-vacuum diagrams CI, and E to the A plus B is E to the A plus B. So now I have E to the sum over vacuum diagrams of CI, and these terms cancel here. So we're left with what I said, that it's just the sum over I unequal to vacuum diagrams or diagrams with sources of CI. So this is very important simplification. To get our interacting path integral, we just have to take all, we don't have to worry about disconnected diagrams, and we don't have to worry about vacuum diagrams. We just take all the connected diagrams with their symmetry factors, sum them up, and get, because remember we took care of, a long time ago, once we established this, that the symmetry extra symmetry factor was the product over I of ni factorial, that enabled everything to exponentiate. That was very convenient. And now we just have this, we don't have counter terms in here yet, but we have everything but counter terms, and we just take the connected non-vacuum diagrams and exponentiate. And that's our interacting path integral for now. So I will see you next time. We'll start to talk about how we handle the counter terms, and some more about how this all works. Thank you very much for watching. Bye-bye.